Okay, what we are going to start out with is a little bit of review before we get to the Fourier part. Specifically, we are going to review even and odd functions. Thank you. Anybody remember how to check if a function is even, both algebraically and geometrically? It is, yes. Symmetric about the y-axis. That's the geometrically part. Algebraically? No. Correct. So if we make x negative, we should still end up with f of x. That will tell us that a function is even. What about an odd function? Again, both geometrically and algebraically. Symmetric about what? About the origin. And then algebraically, how do you show that a function is odd? F of negative x will give you negative f of x. Okay, few properties that you need to know or remember. Product of two even functions is even. Product of two odd functions is also even. Product of even and odd functions is going to be odd. So these should be pretty intuitive. The sum or difference of two even functions or two odd functions is also even or odd. Does that make sense with all the parentheses?
Yeah.
So like the difference of two odd functions is odd. The difference of two even is even. Okay. Here are the two that are going to be the most helpful to us today. If we have a function that is even, and we are taking the integral from negative a to a of f of x dx, that is the same as taking the integral from 0 to a of f of x dx and multiplying by 2. F is odd, then the integral from negative a to a of f of x dx is going to be 0. So that's stuff that you should already know. Even and odd functions are going to help simplify Fourier a little bit if you have a function that is even or odd because of E and F, these properties above. So today what we're going to do is we're going to introduce cosine and sine series. So let's first consider the case where f is even. Okay, if f is even, from yesterday, a sub 0 was 1 over p, the integral from negative p to p, of f of x dx. Because f is even, though, this becomes 2 over p, the integral from 0 to p of f of x dx. A of n from yesterday was 1 over p, the integral from negative p to p of f of x times cosine of n pi over px dx. Okay. F of x is even. What about cosine? Also even. This whole product then is still even. So this will become 2 over p, the integral 0 to p of f of x cosine of n pi over px dx. So none of that seems super helpful, but what we do next is going to be helpful. B of n is 1 over p, the integral from negative p to p of f of x times sine of n pi over px dx. Sine, even or odd? Odd. F of x is still even. Product of an even and odd function is odd, which means that b of n will be 0. This is a similar idea for odd functions. We're not going to go through deriving, and I'm just going to tell you what the result is for an odd function. Part of your homework is going to be identifying even and odd functions. Do you guys think that you're okay with that?
If b of n is, this is if f of x is even, right?
Correct. Okay, so here are your two definitions of a cosine and a sine series. The Fourier series of an even function f that is defined on the interval negative p to p is called the cosine series. Cosine series is going to be f of x equals a sub 0 over 2 plus the sum from n equals 1 to infinity of a of n cosine of n pi over px. So all I did is rewrite the Fourier series from yesterday, but kept b of n to be 0. So then a of 0, like we already wrote, is 2 over p, the integral from 0 to p of f of x dx. And a of n is 2 over p, the integral from 0 to p of f of x cosine of n pi over px dx. That's our cosine series. That's for an even function. Now, if we have an odd function, if we find the Fourier series of an odd function, this is called the sine series. Okay, you should be able to intuitively figure out the sine series. If we look up here, if f of x is odd, a of 0 will be 0. If f of x is odd, cosine is even, so a of n then will be 0. So the sine series is really nice because all you end up with is b of n. So sine series will be f of x equals the sum from n equals 1 to infinity of b of n sine of n pi over px. B of n is 2 over p, the integral 0 to p of f of x sine of n pi over px dx. Quick point for us to know is at x equals negative p, 0, or p, at any of those 3 points, sine of n pi over px x is going to be 0. So the series converges to 0 at these points. Okay, here's our first example. We are going to expand the following piecewise function into a Fourier series. Okay, so what we could certainly do is we could expand this in a Fourier series like we did yesterday. But if this function happens to be either even or odd, we could use a cosine or a sine series. So that'll be a little bit quicker. If we sketch this out, this is what our function looks like. Symmetric about the y-axis means that this is going to be an odd function. So odd function, we can use a sine series then. What?
It's symmetric about the y-axis.
Yeah, this is symmetric about the y-axis, isn't it?
Would it be either?
Or about the origin. Oh, no, okay, I spoke wrong, but it is odd still.
Yeah.
Symmetric about the origin, but it's odd, which means it's odd. With me? Okay, great. So we're going to use a sine series. So our b of n then is going to be 2 over p. What is p in this case? Pi. And that's because we're defined from negative pi to pi. So we have 2 over pi, the integral from 0 to pi. F of x from 0 to pi in this case is 1. So we get 1 times sine of n pi over p x dx. So those pi's cancel, so we're really just integrating sine of nx. So this will be 2 over pi. Integrating sine of nx, we end up with negative 1 over n cosine of nx from 0 to pi. So this ends up being negative 2 over n pi times cosine of pi n minus cosine of 0. Okay, I believe this came up on your homework last night, but we didn't necessarily talk about it in class. Cosine of 0 is 1. Cosine of n pi either going to be 1 or negative 1. So a way that you can express this is negative 1 to the n. So if n is 1, it would give us cosine of pi, which would be negative 1. If n is 2, that would be cosine of 2 pi, which would give us positive 1. So this is going to be negative 2 over n pi times negative 1 to the n minus 1. Possibly a nicer way to write this would be 2 over n pi times 1 minus negative 1 to the n, just so that that's positive. Doesn't really matter, but it just looks a tiny bit nicer. So then our Fourier series is going to be the sum from n equals 1 to infinity of that b of n times sine of n pi over px, which in this case will be just nx. Because that'll end up being 0 because the function is odd. Okay, so in your homework, the first half, you're going to have to identify if a function is even or odd. Second maybe not the second half. After that, you're going to have to expand in a Fourier series. So you're going to have to do what we did here, identify if the function is even or odd, and that will help you pick if you're using a sine or a cosine.
How did you know that f of x was 1 and not negative 1?
Because we're integrating from 0 to pi.
Okay. Thank you.
Mm-hmm. Okay, anything else? Okay. Is that enough practice with cosine and sine series? Right. Here's my plan. We have one more very long problem that has 3 problems in it. So we're going to get through what we can today. We'll finish what we didn't finish today tomorrow, and then tomorrow I will let you have the rest of the period to work on your homework. Does that work for us? Okay. Next thing we need to talk about is what's called a half-range expansion. Okay, so what we looked at between yesterday and today. So previously, yesterday, today, we looked at f defined on in a interval negative p to p. What we need to address next is what happens if we're only defined on 0 to p, not negative p to p. So what happens if f is defined on 0, instead of p, L is normally what's written. And you'll see why in a minute. But what happens if we start at 0 now instead? What we're going to need is we can't ignore the negative L to 0. We can't ignore the first part of the interval. So we're going to need something there. We're going to need some definition there. We're going to need to define f of x, and there's 3 different ways that we can do that. So we need to supply an arbitrary definition of f of x on the interval negative L to 0. There's 3 different logical ways that we can do this. First case is we can make f even on negative L to L. Logically then, alongside that, we can also make f odd. Or we can define f on negative L0 by y equals f of x plus L. And I'll show you what that looks like in a minute. Okay, so I'm going to draw these in order. So this is going to be case 1, case 2, case 3. So let's say that our function looks something like this. Case 1, I want to define f between negative L and L, and I want f to be even. So my other half of f would look something like this. So then f would be defined between negative L and L. I also could make f odd, so I could make it symmetric about the y-axis, or about the origin rather. Case 3 means that f is periodic with a period of L. So it means every L it's repeating itself. So this is the kind of different case. Okay, so cases 1 and 2 in this case. These cases will yield cosine and sine series. These are known as half-range expansions. Okay, so the last example we have to do. We are going to look at a function that is defined between 0 and L, and we are going to consider all 3 cases. Ready?
Why do we consider all 3 cases?
Just so that you can see what it looks like. So in your homework, you'll be told most of the time to do sine and cosine, or one or the other, yeah. Okay, here's the function we're going to consider. We are going to expand f of x equals x squared, x between 0 and L, in first a cosine series, then a sine series, then a Fourier series. So these correlate to cases 1, 2, and 3. Okay, cosine series. First thing that we need to identify is what is P. So if we look back at case 1, we're defined from negative L to L. What is P in this case? L. Okay, so our a sub 0 then is going to be 2 over L, integral from 0 to L, of f of x dx. Right, that's just a cosine series. It's what we wrote on the previous page. Are you guys okay if I just tell you what that ends up being? Okay, great. That is 2/3 L squared. Okay, so then next, we have to find a of n, again from when we wrote this down before. It's going to be 2 over L, the integral from 0 to L of f of x, so in this case x squared, cosine of n pi over p, p in this case is L, x dx. Okay, this one's going to be tedious. We're going to have to do tabular here. So we have cosine of n pi over Lx. That's the one that we're going to have to integrate. So this will be L over n pi sine of n pi over Lx. And then negative L over n pi squared cosine of n pi over Lx. And then negative L over n pi cubed sine of n pi over Lx. And I believe that that's all I'm going to need. So then differentiating x squared, I get 2x to 0. Okay, so this ends up being 2 over L times the quantity. X squared L over n pi sine of n pi over Lx plus 2x times L over n pi squared cosine of n pi over Lx. Subtract 2 times the quantity L over n pi cubed sine of n pi over Lx. All of that being integrated or being evaluated from 0 to L. Okay. So we get 2 over L. Plugging in L, I'm going to have L squared times L, so L cubed over n pi sine, plugging in L, so sine of n pi, Plugging in L, I'm going to have L times L squared, so 2L cubed over n squared pi squared. Cosine, plugging in L, that'll be cosine of n pi. Minus 2 times L over n pi cubed sine of n pi. Plugging in 0, because of the x, this will be 0. This will be 0. Sine of 0 will be 0. Okay, sine of n pi is 0, so those two are gone. So then we get 2 over L times 2L cubed over n squared pi squared, cosine of n pi. So we get 4L squared over n squared pi squared, cosine of n pi. So we talked about cosine of n pi is either 1 or negative 1. Cosine of n pi we can replace by negative 1 to the n. So this gives us an a of n, bless you, of 4L squared over n squared pi squared times negative 1 to the n. So finally, yes?
Wouldn't you, when you plug in your 0 in it, the cosine be 1? No, we'll do about 2x.
Because the 2x in front.
I have a question.
Thank you.
So in your vocabulary,
Mm-hmm.
your last one, wouldn't it be positive L over n pi cubed sine because the derivative? Oh wait, no, it's the integral. Sorry, I don't know what I was thinking. Sorry.
You're all good.
Would those not cancel? Because it's L squared over n pi minus 2.
But sine of n pi is 0. So they don't cancel,
yeah.
they're both 0. Anything else? Okay, so finally then, cosine series. It's going to be a0 over 2, so that 2/3 of L squared, divide that by 2. So we get L squared over 3, or 1/3 L squared. Okay, in the book, a lot of times they're going to pull out anything that doesn't have an n in front of the integral. So a lot of times they'll pull out that 4L squared over pi squared. Not the integral, the summation. So that leaves us then with negative 1 to the n over n squared, cosine of n pi over Lx. Okay. Are we ready for the sine series now? Good, I am too. Okay, so if we go to the sine series, again, looking at the picture, we are now defined from negative L to positive L, like negative P to P. So P in this case is still L. Now, I keep telling you that because when we get to case 3, P is no longer L. Because in this case, we're repeating quickly, more quickly. Okay, so if P is L, our B of n then is going to be 2 over L, integral from 0 to L, of f of x, so x squared, sine of n pi over P, which in this case is L, x dx. Okay, this one's going to be a little more tedious. Again, we're going to have to do tabular. So this will be sine of n pi over Lx, negative L over n pi cosine of L. Thank you. Hi. Okay, so combining all of that then, we get 2 over L times the quantity negative x squared L over n pi cosine of n pi over L x, add 2x L over n pi quantity squared sine of n pi over L x, add 2 times L over n pi cubed cosine of n pi over L x. We need to evaluate all of that from 0 to L. Okay, so starting with plugging in the L. Here I'm going to have L squared times L, so negative L cubed over n pi cosine, if I plug in L, cosine of n pi. Here I'm going to have 2L times L squared, so 2L cubed over n squared pi squared sine of n pi. If I plug in L here, I'm going to have 2L cubed over n cubed pi cubed cosine of n pi. If I plug in 0 because of the x, this will be 0. Because of the x, that'll be 0. So I have plus 0 minus 0. If I plug in 0 here, cosine of 0 is not 0, so here's where you need to be careful. You'll end up with minus 2L cubed over n cubed pi cubed. Okay. Already talked about sine of n pi, that's going to be 0. So that's gone, so we can ignore all that stuff. So we end up with 2 over L times negative L cubed over n pi, add 2L cubed over n cubed pi cubed, cosine of n pi, subtract 2L cubed over n cubed pi cubed. Okay. This 2 over L we can distribute in, we can leave it out. I chose to distribute in, so that's what we're going to do. So if I distribute this in, I'm going to end up with negative 2L squared over n pi plus 4L squared over n cubed pi cubed, cosine of n pi, subtract 4L squared over n cubed pi cubed. A few different options here. You can find a common denominator and combine those since they're both being multiplied by cosine of n pi. Other thing you can do is you can combine these two instead. One thing to remember, cosine of n pi is either negative 1 or 1, so that will be negative 1 to the n. What I'm going to do is I'm going to combine that and that. So I have negative 2L squared over n pi multiplied by that cosine, so that'll be negative 1 to the n. Then I have plus 4L squared over n cubed pi cubed. That's being multiplied by the cosine, which is negative 1 to the n, and then minus 1. Last thing that's normally done, normally we don't leave that negative. So if I take that negative 1 and I multiply that in, this will really be 2L squared over n pi, negative 1 to the n plus 1. Okay. Finally, time to write our answer. So that was b of n. So our sine series then will be f of x is the sum from n equals 1 to infinity plus that. All of that is b of n. So it'll be 2l squared over n pi negative 1 to the n plus 1 plus 4l squared over n cubed pi cubed negative 1 to the n minus 1. Bless you. This is a sine series, so that'll still be multiplied by sine of n pi over lx. Now, the book is not going to express the answer that way because the book is going to pull out this 2l squared over pi. So the book will factor 2l squared over pi out of both of those just because they don't rely on n. Okay. How do we feel about cosine and sine series? Tedious, for sure. But you're using the same formulas over and over again. Do we have any questions on what we did today? No. Okay. We definitely don't have time to do the Fourier series part, so tomorrow we'll probably take 15 minutes to finish these notes, and then we'll go over your last exam, and then you guys will have like 20 minutes to work on your homework. Does that sound good?